Welcome to the lecture series on the subject Basic Thermodynamics. This is module 3 in that part 1, second law of thermodynamics, lecture number 2. Myself Dr. Nsatheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So the contents for this topic are thermal efficiency, refrigerators and heat pump, COP, reversible and irreversible process, and irreversibilities. Now let us discuss the thermal efficiency of heat engine. So in the last lecture, we studied about heat engine, which is nothing but a device which absorbs heat from a high temperature reservoir and converts part of that into work and rejects the remaining heat into the low temperature reservoir. Now you can see here the four components representing the four processes of a heat engine. So inside this circle, and it is written heat engine. So the high temperature reservoir and the low temperature reservoir are the external to the heat engine. So the heat engine absorbs an amount of heat QH from the high temperature reservoir, which is maintained at a temperature of TH, and converts part of that heat into work by an amount of W net out and rejects the remaining heat QL into the low temperature reservoir TL. The performance of heat engine is measured by a term or calculated by a term known as efficiency. Since it is mainly dealing with the heat energy or the conversion of heat energy into mechanical energy, so we use the term thermal efficiency for the heat engines. Now here you have to see what is the desired output of this engine and what is the required input. So purpose of the heat engine is to convert the heat energy into the mechanical energy. So we look into work output from the engine, so which is the desired output of the engine. So in order to deliver this output, it has to absorb some heat from the high temperature reservoir, which is nothing but QH, which is nothing but the required input. So the ratio of desired output by required input is nothing but the efficiency, or W net out by QH is the efficiency. Now you are supplying QH amount of heat into the heat engine. So converting W net out into work, rejecting QL, so you can also write that QH minus QL is equal to W net. So this is very important. QH minus QL is equal to W net. Okay. Now I'll write the expression for the thermal efficiency in the next slide. So efficiency or performance is nothing but desired output by required input. So for heat engines, thermal efficiency is equal to net work output by total heat input. So if you substitute, eta TH is equal to, or eta ITH, okay, W net out by Q in. So it can also be expressed as 1 minus Q out by Q in. So now previous diagram I have shown, or I used QH and QL. So in place of QH you can use Q in, and in place of QL you can use Q out also. So then W net becomes Q in minus Q out. So Q in by Q in is becomes 1, and Q out by Q in is written here. Okay. So that is what, if QH is the magnitude of the heat transfer between the device and the source at temperature TH, and QL is the magnitude of heat transfer between the cyclic device and the sink at the temperature TL, so then this can also be possible. You can express it as 1 minus QL by QH or 1 minus Q out by Q in. So anything is possible here. Okay. Now let us understand the working of refrigerator or heat pump. So refrigerator or heat pump are the devices which absorbs heat from the low temperature space and supply to the high temperature space like surrounding media such as kitchen air with the aid of some external work. So all these refrigerators and heat pumps are the work absorbing devices, in the sense they need some external work input in order to absorb heat from the low temperature and supply to the high temperature. Now the four components involved in the process of refrigeration or heat pump are the evaporator, compressor, condenser and the expansion valve. So now let me explain from the evaporator. So this evaporator, as the name implies, wherein the liquid refrigerant or the working substance enters into the evaporator coils and they absorb the heat from the refrigerated space, or the space which has to be maintained at a lower temperature than that of the surroundings. Now your condition is the temperature at which the liquid working substance enters into the evaporator should be less than the refrigerated space. So then only heat will flow from the space to the refrigerant or the working substance. Then only it can absorb the heat. So during this process of absorption of heat, generally this liquid refrigerant or the liquid working substance will be converted into vapor, hence the name evaporator, because during the phase change large amount of heat can be absorbed by a substance. Okay. Now this, for example, it is entering at -25 and coming out as -20. Now if this working substance, which has already absorbed this heat from the refrigerated space, has to be reject this heat to the surrounding air or the kitchen air, so as to once again to be recirculated. But you know that atmospheric temperature is more than means it is plus, and it's around maybe around 25 plus degrees always. So if you pass this heat through the condenser coils directly, and if you expose it to atmospheric air, so it won't reject heat to atmosphere, instead it will absorb heat because it is at a very low temperature compared to the surrounding air. So before you pass it through the condenser coil, you need to increase the temperature and pressure of this vapor refrigerant or the working substance. For that it has to be compressed by passing it through a device called as compressor. Now this compressor is a mechanical device, so which needs some work input from external work input so that it can do the mechanical work of compression. So by that you can see the pressure increases, temperature also increases to, for example, 60 degrees Celsius. Now if you pass this through the condenser coils and make it exposed to the surrounding media such as kitchen air, so easily the heat energy will flow from this working substance to the surrounding air. Now the word condenser is used because here vapor enters, and once it comes out of the condenser it will be in the liquid form, because once again the phase change always results in maximum absorption or rejection of heat. So if you want to reject maximum heat to the surroundings, so you should allow the phase change in the condenser. Now for example, from 60 degrees Celsius it gets condensed into 30 degrees Celsius. Now once again, if you have to pass this to this evaporator coils, just imagine this is at 30 degrees Celsius and your refrigerated space is well below 0 degrees Celsius generally, or very low temperature rather. Okay, so if you pass this to the evaporator coils, so instead of the working substance absorbing heat from the refrigerated space, the heat will flow from the working substance to the refrigerated space if it is applied at high temperature like 30 degrees Celsius. So before you pass this to the evaporator coils, you need to reduce the temperature. For that you have to pass it through a device called as expansion device, where the pressure and temperature reduces so that the temperature will be well below the temperature of the refrigerated space, and then you can pass it through the evaporator coils and you can make it the working substance to absorb the heat from the refrigerated space. So this is how a refrigerator or heat pump works. Okay. Now you have to see how to find out the performance of a refrigerator or heat pump. Now before that, let me tell you what is the difference between a refrigerator and the heat pump, when I can call it as refrigerator and when I can call it as the heat pump. The purpose is very important here. You see, now suppose the purpose is to maintain the temperature of the refrigerated space at a particular temperature and thereby absorbing heat from there and rejecting it to the surrounding media, so then it is called as the refrigerator. So your purpose is to maintain the temperature of this space by continuously drawing heat from there at a particular level. for which it requires some work input. Now in some cases we need to maintain the temperature of this place at certain level. For example, if the surrounding air, for example in cold areas and all, the surrounding atmospheric air may be 5 degrees Celsius or even below that, and wherein you can't live comfortably. So in that case, if you want to have a temperature inside your building or room at a comfortable living condition of 20 degrees Celsius, so you need to heat the living room. But from where do you get the heat? Once again, it has to be absorbed from the surrounding air, which is at a very low temperature, maybe 5 or less than that. Now, so heat is absorbed from the surrounding media, which is considered as a reservoir, but it is supplied to this living room, which otherwise would have been same temperature as that of the surroundings or the atmospheric air. Now, because of this heat supply, so its temperature will increase, and through some proper regulatory measures, you can maintain the temperature at a required level of, for example, like 20 degrees Celsius. So, which also requires the work input. So, your purpose of these two are different. So, refrigerator maintains the temperature of the refrigerated space at a particular level, where the heat pump tries to maintain the temperature of the this surrounding or the whatever the compartment or the cabin or the space at a particular temperature above the surrounding temperature. So here it is maintaining temperature above, but here it is maintaining temperature below than that of the surroundings. Okay. Now we will see the performance of refrigerator. It's the coefficient of performance. So here the performance of heat pump or the refrigerator is measured or found out by a term called as coefficient of performance. So performance is always desired output by required input. So as we discussed in the previous slide, when it comes to a refrigerator, the desired output or the purpose is to maintain the temperature of the cold space at a particular level by absorbing heat from there. So your intention is to draw the heat, because you have to maintain that particular space at a temperature lower than that of the surroundings. So you have to absorb heat from there, continuously you have to draw. So your objective is to draw the heat, which becomes the required output, for which you have to supply some heat to some work to the compressor of this refrigeration system. You see all these four components together, which is enclosed in a circle, so it represents the refrigerator. So this becomes the required input. Okay. So desired output by required input. So it is QL by W net in. Okay. Now it can also be expressed as W net, as all of you know, QH minus QL. So you can write COP of the refrigerator as QL divided by QH minus QL, or 1 by QH by QL minus 1. Okay. So this is how to write the expression for the coefficient of performance of a refrigerator. And coming to the heat pump, so now the purpose is different, as we discussed earlier. So your purpose is to maintain this space at a particular temperature. For that you have to constantly supply heat to that space. So the desired output becomes QH, and the required one input remains same as W net in, same as that of the refrigerator. So COP of HP or the heat pump is QH by W net in, and if you substitute for W net in, so it becomes QH divided by QH minus QL is equal to 1 by 1 minus QL by QH. So COP HP is equal to COP R plus 1. This is very, very important relationship. COP HP is equal to COP R plus 1. Sometimes you may be asked to prove this relation also. So let me prove it in the next slide. COP HP is equal to COP R plus 1. So let me take COP R plus 1 first. Okay. So I will take COP R plus 1, then I will prove it is equal to COP HP. So COP R plus 1 is equal to, COP R is nothing but QL. Okay, just try to understand. This is very difficult to write on this slide. Okay, QH minus QL. Okay, now plus 1 is there. So now take common denominator. So it becomes QH minus QL here. QH minus QL. So numerator QL is already there. So when you do the common denominator, so plus QH comes here, because the denominator I have to write here, which is nothing but QH minus QL. So plus QH minus QL. Okay, so this line should go up to here. So now QL plus and minus QL gets cancelled. So this becomes QH by QH minus QL, which is nothing but COP HP. So this is how you have to prove COP R plus 1 is equal to COP HP. Okay. Now, reversible and irreversible process. A reversible process is defined as a process that can be reversed without leaving any trace on the surroundings. See, a process, is nothing but the change of state, wherein the working substance moves from one state to the another state. Now, if it is a reversible process, you should bring back the system back to its initial state. Okay. Now, here the thing is, you can bring the system back to its initial state very easily, but at the same time, there should not be any trace left on the surroundings. Now, for example, if I consider a piston cylinder arrangement like this, and the rigid cylinder and the piston is flexible to move, let me think that this is the state 1 initially. Okay, I am supplying some Q amount of heat to this. Okay, now because of this, the internal energy of this working substance increases, and pressure also increases. This piston is flexible to move. Maybe the piston is displaced to this level by doing some work to a new state called 2. So some work during this movement of the piston, some work is done on the surroundings by the system. Now here this Q will not be equal to W usually, so the difference amount will be stored in the working substance as internal energy. Now this is moved from state 1 to 2, that means I can show it on the property line like this, 1 to 2. So this is 1, this is 2. Now to reverse this, I have to do W amount of work on the system, and at the same time, once I do that, that Q amount of heat should be coming out, so that system once again come back to its initial state at this point itself, and all the property values are restored or regained at 1. That means 2 to 1 also should move along this path, and it should reach 1, and at the meantime the surroundings also, same amount of heat it has supplied at Q should be obtained back by the surroundings, so that there is no trace left on the surroundings. So in that case, the process is called as the reversible process. But in reality, it is very difficult to achieve the reversible process, and all the processes will be irreversible process. Okay. So that is, both the system and the surroundings are returned to their initial states at the end of the reverse process. This is possible only if the net heat and net work exchange between the system and the surroundings is 0. That is what cyclic integral of dW and cyclic integral of dQ should be 0. That is for the original and the reverse process. As I told just now, plus W initially, then minus W are doing. So plus Q initially, minus Q is removed. So 0. The combined value is 0. So then only the process can be reversed. Processes that are not reversible are called as irreversible process. So irreversible processes are given more importance in thermodynamic field. Continuing, it should be pointed out that a system can be restored to its initial state following a process regardless of whether the process is reversible or irreversible. This is very, very important. Now, you see in the previous example, what I considered, so there is one more factor which is affecting this process. That is, when the piston moves from the bottom to the top, right? I think you can recall that diagram. So some friction will be there between the piston and the cylinder. So because of that, some heat will be generated, and which will be absorbed by the working substance. So its internal energy content will be not exactly delta E plus this frictional heat energy. Now when you do the reverse process, W amount of work, so the Q amount of work will not come out. So you need to do some additional work to remove this extra heat. So there will be from the surroundings, so you are doing extra work and extra heat is also removed. So there will be some changes in the surroundings. That means surrounding cannot be brought back to its initial state. So here system you can bring at any cost. That is what it should be pointed out, that a system can be restored to its initial state following a process regardless whether it is the process is reversible or irreversible. Even though for a irreversible process also you can bring the system to its initial state, no issue. Just now I told you, you can bring. But during the process what is happening? You are doing additional system work on the system and you are removing additional heat from the system. So for surroundings, so there is some trace left out. Okay, so that is the surrounding doesn't come to its initial state. So for reversible process, this restoration is made without leaving any net change on the surroundings, whereas for irreversible process the surroundings usually do some work on the system. So that is what I told you, some additional work will be done on the system to bring it to the original state, but meantime the surroundings will not come to its original state. So this is the major or main feature of a irreversible process, wherein the system can be brought back to its initial state but not the surroundings. So work producing devices such as car engines and gas or steam turbines so deliver maximum work, and work consuming devices such as compressors, fans and pumps consume least work when the reversible processes are used instead of irreversible process. So that is a very important thing. If you want to get maximum output from any device, let it be work absorbing or work producing device, so all the thermodynamic processes which are taking place should be reversible process instead of irreversible process. But ideal case only you can imagine a reversible process. So in reality or actual practice, so reversible processes are not possible. Okay. So irreversibilities, the factors that cause a process to be irreversible are called irreversibilities. Means what are the factors which affects the reversibility or which causes irreversibility in a process. So they are called as the irreversibilities. So it includes friction, unrestrained expansion, mixing of two fluids, heat transfer across finite temperature difference, electrical resistance, inelastic deformation of solids and chemical reactions. So all these lead to irreversibilities. That means makes the process irreversible. So thereby it makes us to get a device deliver less work if it is a work producing device and absorb more work if it is a work absorbing device. So with this I conclude the lecture number 2 of this module and will continue the lecture number 3.